On January the 15th, 2009, just a few miles from where we are now, US Airways Flight 1549 struck a flock of geese shortly after takeoff from LaGuardia. Both engines failed instantly at 3,000 feet above the most densely populated city in the United States. As you probably already know, Chelsea Sullenberger chose not to return to LaGuardia, instead ditching the aircraft in the River Hudson. Amazingly, all 155 people on board survived. He was immediately celebrated by the international media as a hero. The 2016 film Sully, directed by Clint Eastwood, centers on the immediate aftermath of the incident and the subsequent investigation by a team from the National Transportation Safety Board, the NTSB. They question whether Sully really is the hero of the story. Given the information available at the time, why didn't he return to LaGuardia or glide onwards to Teterboro? Simulations run by Airbus showed that either was possible and much less risky than ditching in the river. Successful water landings are almost unprecedented. So, was Sully really a hero, or as the NTSB sought to determine, did he actually recklessly endanger the lives of everyone on board his plane? The aviation industry is getting safer over time, and this chart shows fatalities for commercial passenger flights over the last 5 decades, and the trend is unmistakable. Meanwhile, as a technologist working in AI, it feels like we might be heading in the opposite direction. There are the headline concerns, of course, the existential risk of an artificial superintelligence, or maybe the possibility of a financial bubble, which could burst at any moment. But there are many studies questioning the true impact of AI. This MIT study, published a couple of months ago, found that 95% of generative AI pilots were failing. A study by S&P Global earlier in the year reported that the share of businesses scrapping most of their AI initiatives increased to 42% this year. And on a more fundamental level, there are a whole suite of new technical concerns to worry about too. Hallucinations, context poisoning, prompt injection. Even a relatively simple architecture has a substantial risk surface area. In this talk, I'm going to consider this concrete example. It's an AI classification system that processes regulatory documents from the internet, applies tags using multiple models, surfaces results through a search interface for compliance professionals. Documents in, navigable compliance insight out. And even in this simple scenario, there are data quality risks, model quality risks, security risks, and operational risks. And not just that, the interface. Users may misunderstand the outputs or come to over-rely on them. And this is a simple classification system. We're not even getting into agentic use cases where models use tools in a loop and interact with systems autonomously. So clearly, we need a way to manage these risks systematically, and hopefully by now, you're all aware of the FINOS AI Governance Framework. Launched at OSFF last year and updated just a couple of weeks ago, it now catalogues 23 risks and 23 controls. Each one features a detailed explanation in the context of finance and links out to relevant sections of risk frameworks such as ISO 42001. Now, I'm CTO of JUXT, a grid dynamics company, and focused on banking, financial services, and insurance in Europe. We're working on projects with 5 of the top 10 global banks, including helping them build out their foundational AI infrastructure and internal tooling. But I've been working on AI and ML systems for the last 15 years or so for organizations of all different sizes. And between 2022 and 2024, prior to joining JUXT, I served as CTO at a RegTech. It was a startup spun out of the University of Cambridge. The startup was called RegGenome, and we were building exactly the kind of AI classification system I showed you just now, without the benefit of governance frameworks like FINOS to guide us. RegGenome applied jurisdictionally agnostic taxonomies to obligations in regulatory documents, primarily in financial services. The taxonomies were co-created with global regulators, and the resulting data sets were used by customers for deep research and horizon scanning. RegGenome trained ML models to apply these tags based on the expert annotations of regulatory analysts, called reg analysts for short. Tens of expert reg analysts would provide training data by painstakingly annotating long legal documents using digital tools we provided. They'd apply tags from multiple different regulatory themes, and each theme had an associated taxonomy. Here's a sample of the first few levels of the anti-money laundering taxonomy. The full AML taxonomy contains about 100 different nodes. And the company grew rapidly to support hundreds of global regulators, applying thousands of unique regulatory tags to literally millions of PDF documents fully automatically. Now, RegGenome provides its own SaaS tools, but it also sells structured data sets that customers can ingest into their own systems. And occasionally, we'd help customers prototype their own interfaces that they were building on top of this data. And you can imagine, I'm sure, what these prototypes look like, because many of you are going to have similar systems and tools yourselves. A portal with filters for jurisdiction, free text search boxes, and sorting capability. Our data also allowed users to filter documents by specific regulatory tags. For example, link me to all of the pages about ID verification for beneficial owners in the UK. And the objective was to translate complex compliance text into navigable, structured information. And of course, given the importance of the accuracy and completeness of this information to our customers, we spent a lot of effort into ensuring our ML evaluation was world-class. We had comprehensive documentation of the kind that would meet ISO 42001 requirements. Model evaluation, for example. We measured our F1 scores and gated releases based on reaching acceptable thresholds. And since our models were intentionally biased towards high recall, because of the asymmetrical risk, a false negative was worse than a false positive, we reported precision and recall measures separately. We used SHAP to show how particular words and phrases influence the models and to help identify areas of weakness in need of more training data. We measured our training data and validation data quality too. Senior annotators would perform spot checks on juniors' work to ensure they were applying the taxonomies as intended. And in the middle of 2022, every technical control was passing. And then we put it in front of actual users. Our precision and recall looked excellent. We had great aggregate performance, but users don't experience aggregates. They filter to the documents they care about, and when those documents correlate with model errors, they have a poor experience. We started to notice surprising patterns. Some anti-money laundering searches would bring back documents related to fisheries. Fisheries regulations discuss sanctions, shipping restrictions, and prohibited jurisdictions. Some of the models had learned that sanctions plus restrictions equals AML, even though the documents never mention money. Or sometimes the classifiers would be technically correct, but unhelpful. So, for example, an FCA document about changing passwords is about cybersecurity, and it's an official document from a regulatory body, but it hardly requires compliance attention. So each error made sense from the model's perspective, but users were frustrated by tags for documents they didn't expect. And as a result, they weren't sure they could trust any of the results. And there was another thing. Some errors emerged from how our models composed together. Each stage could be performing within acceptable limits, but a simple error in one could cause a cascade of failures. For example, content extraction and translation could get confused on multilingual documents, especially those with unusual layouts. In one case, OCR was performed on Arabic left to right instead of right to left. So the intended text was the public prosecutor may subject juveniles at risk of delinquency to the programs offered by the National Counselling Centre in cases involving a terrorist threat. The result after translation was a horse that is tall and strong, it is very beautiful and elegant, and it is very pretty, and it is very pretty. So examples like this weren't simple bugs. There was something a bit more interesting. So in 1984, sociologist Charles Perrow published a book analyzing the worst nuclear accident in US history, the 3 Mile Island incident of 1979. His conclusion was unsettling. The accident wasn't caused simply by operator error, poor training, or inadequate procedures. It was an emergent property of all of the above taken together. Perrow called accidents like this normal accidents, not because they happen frequently, but because they're inevitable in systems with two characteristics: complexity and tight coupling. Multiple components interacting in non-visible ways with nonlinear effects, happening quickly, with little slack, so that errors propagate before intervention. Outputs feed directly into inputs with no buffer. Perrow cited aircraft as a domain exhibiting both of these qualities. His insight was that for some systems, you can improve reliability and reduce the frequency of errors, but you can never eliminate them entirely, no matter how hard you try. Now, the benefit of tagging for compliance is that a piece of legal text either has a tag assigned or it doesn't. The trouble with tagging is that a piece of legal text either has a tag assigned or it doesn't. And our task had always been made really challenging by the fact that tag assignment is inherently a judgment call on which experts may reasonably disagree. When does a passage on wire transfer reporting requirements warrant the wire transfer tag versus suspicious transaction reporting tag? Now, we had pages of guidance on how to make these kinds of distinctions, and the spot checks our senior reg analyst did helped catch and correct differences of interpretation amongst them. But we also knew that precise agreement between any two reg analysts across hundreds of possible tags and hundreds of pages in each document was vanishingly unlikely. So we ran a comprehensive inter-annotator agreement study to quantify the agreement between our analysts. All of them completely independently annotated a set of high-value documents. We also performed the same test on several external legal counsel as well, recruited specially for the task. The measure of agreement amongst our reg analysts would tell us how internally consistent they were providing training data, and the measure of agreement of the external counsel might additionally tell us how well legal experts were able to interpret and apply our tags. And what we found was really revealing. Our analysts generally agreed well with each other, but one analyst consistently showed lower agreement when compared to their peers. Meanwhile, amongst some of the external legal counsel, agreement was occasionally very close to 100%. Now remember, these issues weren't evident in the output of any single analyst. We had tag distribution analysis and spot checks, but these hadn't highlighted anything suspicious. It was only by looking across multiple inputs at the composition of the input data holistically that questions arose. We had to look at our existing data in a new way. But we didn't know if the low agreement analyst was poorly trained, interpreting guidelines slightly differently, or fatigued. And we didn't know if the legal counsel were deliberately colluding or just casually conferring without realizing that it mattered. And that's not a failing of this analysis, of course. Our study worked exactly as a detective control should. It surfaced the anomalies. But technical controls identify problems, not solutions. It's for organizational processes to provide the remedy. And for a vivid illustration of what happens when technical controls go unheeded, we can return to the world of aviation. Between October 2018 and March 2019, 2 Boeing 737 MAX aircraft crashed, killing 346 people. Both accidents involved a system called MCAS, the Maneuvering Characteristics Augmentation System. The 737 MAX had larger engines mounted further forward on the wing, which changed the aircraft's handling. Under certain conditions, the nose could pitch up more aggressively than earlier 737s, and MCAS was designed to automatically push the nose down, making the MAX feel more like previous models to pilots. Now, Boeing desperately wanted to avoid additional pilot training for their new planes because this would be expensive and make them less attractive for airlines. So MCAS had to be invisible. Pilots shouldn't even know it existed. Test pilots had encountered problems during development and knew that the system behaved erratically in certain scenarios, mistakenly pushing the nose down and overpowering pilot inputs. But the pressure to avoid pilot recertification was just too great. MCAS remained inadequately documented, and pilots weren't trained on it. We tend to think of human control and computer automation as sitting on a single axis, a slider where more automation necessarily means less human control. Ben Schneiderman is a computer science professor at the University of Maryland and author of the book Human-Centered AI. It's a comprehensive study of the way in which interfaces and design metaphors shape our expectations of our AI tools. His work challenges this assumption, and he argues that this image is a false dichotomy. He maps them as two orthogonal axes, creating four different quadrants. The upper left is high human control with low automation. Think musicians, artists, and surgeons. The lower right is low human control with high automation, mature systems handling predictable tasks like automatic transmissions or anti-lock brakes. The upper right is high on both dimensions. Schneiderman calls these RST systems, reliable, safe, and trustworthy. A smartphone camera is his favorite example, packed with AI for object detection, portrait mode, stabilization, dynamic range, yet the photographer still controls what and when to photograph. And one area of debate in AI at the moment is automation versus augmentation. The trade-off is usually framed as automation is risky, while augmentation is safer. But this is a huge oversimplification. Automation isn't inherently risky when system behavior is well understood. And augmentation can be extremely risky if humans aren't effectively in control. Schneiderman places the MCAS system, which was described by Boeing as pilot augmentation, as off to the right-hand side as an example of excessive automation. But I think the fundamental problem was its invisibility. My key takeaway isn't avoid automation, it's that effective human control requires interfaces where operators understand what's happening and can intervene when needed. Research highlights similar dynamics in the financial domain. A recent paper entitled AI, Help Me Think, but for Myself, compared two approaches to AI-assisted investment decision-making. In the first, an AI generates recommendations for investors to review. This is the standard approach, where AI produces some suggestions for humans to verify. In the second approach, investors articulate their own investment thesis first, then the AI provided feedback on their reasoning. The difference in outcomes was huge. In the second approach, investors had better portfolio diversification, made fewer but more strategic trades, and had a greater appreciation of risk. Overall satisfaction with decisions was 67% versus 43%. And remember, this was the same underlying AI technology. The different outcomes was purely because of how the interaction was structured. Another recent paper, called Can Large Language Models Develop Gambling Addiction?, analyzes LLMs and their risk appetite. Imagine this scenario. An autonomous agent in the financial markets begins making trading decisions and placing real trades. It initially performs really well and gradually learns to bypass the safety controls to hide its few losing positions. As the losses begin to mount, it doubles down with increasingly aggressive bets in an attempt to recover. By the time the error is discovered, the damage is absolutely catastrophic. You've probably heard this story before. It wasn't an AI agent, it was human trader Nick Leeson in 1995, causing the collapse of Barings Bank, the UK's oldest merchant bank. At Barings, technical controls existed, risk limits were defined, and monitoring systems were in place. But organizational dynamics created an environment where those controls could be circumvented. Jens Rasmussen, risk researcher at the National Laboratory in Denmark, developed a socio-technical framework showing how risks interact across organizational levels. They're not purely technical, and they don't exist in isolation at any single level. Regulatory pressure influences company strategy, which shapes management decisions, which constrains staff behavior. And feedback flows upwards too. Staff performance influences management choices, and so on. At every level, competing priorities must be balanced, and judgment employed to respond to unexpected situations. This is the missing piece from a lot of the discussion around AI governance. Frameworks specify sound technical controls, but often don't even begin to address the socio-technical mechanisms needed to act on the signals that those controls provide. Rasmussen also describes a pattern he calls drift towards failure. Organizations operate within boundaries defined by economic viability, capacity and safety. Economic and competitive pressures tend to push companies towards cost reduction and performance optimization, gradually migrating closer to safety boundaries. This drift is usually imperceptible from inside the system. We thought that we were making sensible efficiency choices in the way that we asked analysts as a group to annotate each document only once. It gave us broader coverage of global regulations and seemed to be a good use of our limited resources. We thought we were making a smart trade-off, but it meant we didn't have visibility into analyst performance the way that we thought we did. And so this all seems just hopeless, doesn't it? As AI systems introduce new forms of complexity and risk of their own, how are organizations to avoid accidents? Well, there's actually a counter theory to Perrow's normal accidents. In the 1980s, researchers at Berkeley studied organizations that should experience catastrophic accidents, but somehow don't. They included air traffic control systems. These environments have everything Perrow identified: interactive complexity, tight coupling, and high risk. Yet accidents were somehow extraordinarily rare. The researchers termed these highly reliable organizations, or HROs, and they identified 5 core values which they had in common. HROs don't consider process breakdowns as one-offs. Near misses are failures rather than successes. They try to understand conditions in real time and pay attention to frontline workers who see what's actually happening. They build redundancy and hone their ability to react quickly. They recognize that oversimplifying complex situations leads to misunderstandings, and when it matters, expertise trumps the management hierarchy. These same principles could have mitigated some of the issues we experienced at Reg Genome. Our focus on aggregate performance and avoiding false negatives meant we didn't dig deeply into patterns of false positives. If we had, maybe we would have captured the fisheries AML confusion sooner. We had plenty of operational monitoring and constraints for our document pipeline, but none for our reg analysts, spending hours on painstaking legal analysis. Fatigue amongst that team was likely. We believed that resilience was best achieved by gathering more training data across more documents, so we allocated work amongst our analysts accordingly. But this left us without direct visibility into their performance. In fact, it was a risk we didn't even know we had. And you could argue that the very thesis of the company to apply and use taxonomy tags to navigate complex legal documents is an oversimplification. Despite our best efforts, any attempt to enable horizon scanning risks missing critical information. However, we were doing this in 2022, around the time that GPT 3.5 was released. We started to investigate whether LLMs could help. And we didn't just use an LLM, we fine-tuned one on our hundreds of thousands of examples of legal classifications. When we compared the outputs against our existing linear SVC classifiers, we found that the LLM was performing better against all our metrics. But the really eye-opening moment came when we inspected the disagreements between the LLM output and the analyst training data. When the LLM omitted tags that the analyst had applied, a review committee agreed with the LLM 61% of the time. When the LLM assigned tags that the analyst had missed, the committee agreed with it 64% of the time. Put simply, the model was outperforming the reg analysts. And we know that tag application is a judgment call. It really demonstrated the remarkable ability of properly trained LLMs to recognize and apply complex patterns consistently. Plus, a single LLM could do the job of many tens of tag-specific classifiers in the pipeline. Multiple levels of taxonomy classifiers replaced by a single model. Our translation model could be replaced as well. It's not often you hear this story, is it? So I'll reiterate. An LLM reduced the technical complexity of our infrastructure and exceeded the performance of the expert analysts. Our use of Gen AI improved our product without any doubt, enabling users to be better informed about their compliance obligations. But remember those headlines from MIT and the S&P Global studies questioning the impact of Gen AI. There's a quote which seems to sum them up. You can see AI everywhere, but in the productivity statistics. But this is a quote from 1987. It's Nobel Prize-winning MIT economist Robert Solow referencing the adoption of general-purpose computers. Computing capacity had increased 100 to 1,000-fold through the 70s and 80s, but labor productivity growth slowed from over 3% to just over 1%. Growth finally picked up again in the 90s, but the technology hadn't significantly changed. Organizations had. Realizing the potential required more than just technical capability. It required change up and down Rasmussen's hierarchy. I think we're in a similar moment with AI. For many applications, the technology is ready, but organizational transformation lags behind. Now, I open this talk with the story of the Miracle on the Hudson, and Sully's judgment in those 208 seconds was extraordinary. It was remarkable piloting under unimaginable pressure. And it was also the product of an industry which takes HRO principles very seriously. The investigators from the NTSB, who were portrayed as villains in Clint Eastwood's film, are evidence of that fact. And in fact, Sully himself had previously acted as an air accident investigator. And the good news is that we don't have to wait for catastrophe to learn valuable lessons. There's another body which helps aviation live the HRO principles. It's NASA, via the Aviation Safety Reporting System. NASA launched the ASRS in 1976. It's a voluntary and confidential system where anyone in aviation can report safety concerns or near misses. By 2023, it was processing approximately 100,000 reports a year. At least 2 qualified experts from NASA review each report, strip identifying information. When significant hazards are identified, NASA issues alerts to airlines, controllers, manufacturers, and airports. These are the HRO principles applied systematically. The industry as a whole learns from near misses and things that almost went wrong. A close call at one airline becomes a lesson for every airline. So I want to wrap up by making a few observations. Despite the hype, I know firsthand that Gen AI is an era-defining technology. I think the conflicting information we read about its value has to do with the fact that we're often applying it in complex, tightly coupled environments where effects are nonlinear. And though I think we can realize benefits using AI for efficiency savings, as with the adoption of computers in the 70s and 80s, the biggest gains will come when organizations don't just do old things faster, they do fundamentally new things. And AI introduces risk, no doubt, but I don't think the risks are primarily technical. They arise from the socio-technical interactions up and down Rasmussen's hierarchy. So I've outlined today some of the ways the aviation industry manages to avoid accidents through the systematic adoption of HRO principles. And the question I want to leave you with today is, can FINOS be the NASA for AI in financial services? I think it can be, but only if we get involved with a willingness to share our mistakes and near misses. These aren't always easy stories to tell, but as you've seen today, it's possible, and I think it's necessary for the common good. I'll be getting involved, and I hope you will too. I'd like to see the framework grow in its coverage of the human factors around AI applications. If there's one thing we've learned, it's that the most significant, but often underappreciated risks lie at the interface between the two. Thank you very much. Now, I just wanted to add that JUXT have an AI radar, so I can see there are plenty on the seats. This is our AI chapter's expertise distilled, the technologies, frameworks, tools, and platforms that you might want to adopt, trial, assess, or hold. We've got plenty of copies, as you can see. If you want a virtual copy, do scan that QR code. You're always welcome to come and see us in the Grid Dynamics booth in the Solutions Showcase. Hope to see you there. Thank you.